We'll start the recording. So for this question, the two variables that we tend to deal with, one is the mass of the additional mass that we're going to place on the end point of the wooden strip, and the angle at which the toppling actually occurs. These two can be interchangeable. I'll tell you why. Because if you think about the procedure of the experiment, whenever we'll be doing the experiment physically, it is possible that we can attach a fixed amount of mass and slowly increase the value of the theta to find out exactly at which theta the block actually topples over. We can this is possible to achieve because this strip is capable of rotating about that nail position. Or we can do one thing is that we can have some predefined angles. For example, let's say we can have let's say 10, 20, 25, 30, 35. We can have some increments of 5s or 10, or it can work for 60 degree. For 6 different values, we can have multiple different angles, predefined angles, and then we can have variable amount of mass that can be added. Now, if you ask me, what I personally would like is to have the m as a independent variable and the theta to be a dependent variable. I'll tell you why. It is possible. Let's say if you give a fixed amount of mass on the end of the strip, I'm telling you my preference, but it can vary from our scheme. Whenever we'll be increasing the theta slowly, it is possible for us to increase the theta by even by the slightest amount of increment, because this is a continuous variable. We are rotating the strip. So you are not going to run into trouble of discrete increment. So it is possible to find out the exact theta value for which the mass gives you the toppling effect. It is possible for you to find that out. Exact theta, I'm meaning the exact precision of value of theta, which you can measure by a protractor, or in this case, this would be much better if we do find it by some set square and by some trigonometric method. For example, hypotenuse by vertical distance or hypotenuse by base. So or any of the trigonometric ratio, sin cos theta, sin cos or tan. Measuring angles with trigonometric values always makes sure that we get better precision compared to the protractor, because protractor is always, typical protractors are always graded in 1 degree. So you have a uncertainty of plus minus 1 degree. Whereas if you go for the trigonometric method, you basically measure the lengths and then you finding out the ratio from the mathematical output. So that can give you a fraction of values, which is more dependable. So we can find out the exact value of theta for which the block actually topples over. This is possible to achieve, number one. However, on the other hand, if we predefine some theta values, let's say we're gonna mark some predefined values, and then we're gonna slowly add up mass to the end of this strip and find out for exactly which mass is gonna topple over. This would require us to have very small increments of mass. For example, the typical laboratory masses that we work with, the smallest mass that you can have access to is 5 gram. These are the smallest of the masses, and not smaller than that. In very precision case, you can get 1 gram mass set, but they're pretty rare and not so very readily available. You might not have ever seen a mass set where you actually have access to 1 gram size of mass. So the problem is that even if you have the minimum value of your mass is 5 gram, you will have to increment the value of that hanging mass with a step size of 5 grams. So let's say for a certain angle, let's assume, let's say 25 degree. Let's say for 25 degree, the toppling is happening at, let's say 65 gram, but it is not happening at 60 gram. So there is no way for you to exactly precisely find out that exactly for which value of the mass the block is actually toppling over. You're definitely sure that it is bigger than 60. You can definitely sure it is either equal to or less than 65. So it could be any value in between. It could be 61, it could be 62, it could be 62.5, it could be 63.7. It could be any of these values in between for a specific angle value. But because you are limited by the value of increment of the mass, you can never exactly precisely find out the precise mass for which this toppling effect is going to occur. That's just my predicament. So if I was doing this experiment can be done by both of these variables interchangeably. This is true. But if I was doing this experiment, I would go for a fixed mass, which would be my independent variable. And then I would go for theta value. I will increment the theta values so that I can work with it. One of the important things that is that can be said over here as well, whenever I'm working with my theta values, I should preferably have the strip. Initially I should have the angle theta at a pretty high angle, possibly the highest amount of angle that I'm gonna achieve it for. What I need you to understand that whenever the theta is large, then you're gonna require a bigger mass because you're gonna have smaller perpendicular distance, so the moment would be less. So that's the given. You should understand this from the basic idea of turning effect. So whenever this angle is bigger, this mass would be closer to the center of gravity of the block, so you would require a bigger mass for the toppling of it to occur. But whenever the theta is less, for example, whenever this bar is almost horizontal, then you would require a much smaller amount of mass. So the way I would preferably do this experiment is first set up this theta at a significantly high angle. For example, let's say 60 degree. That's the maximum theta angle I'm going to work with. If you wonder why does the 60 come from, that's just a personal choice. You can also go with 70. But the bigger amount of angle that you're going to work with for your maximum value, the bigger amount of mass you have to deal with. So that's a bit thing, an important thing for you to achieve. So I'm gonna let's say align this thing at about let's say 60-degree angle. Then I'm gonna slow. Just a second. আমি একটু বলে নিই তারপর আমি কোশ্চেন নিচ্ছি। হাত উঠায় রাখো। So then I'm gonna slowly add up mass to this point and try to find out for exactly how much mass I'm having this toppling over. So whenever the block is is toppling over for a certain addition of mass on this strip, I would be flexible to change the angle a slight bit to find out that exact mass for which the toppling over occurs. If you wonder how do I find that out, it's altogether a bit of a trial and error process. So you keep on adding the mass. For a certain mass, you'll see that the block is toppling over. Then you slowly adjust the angle to find out the exact sweet spot that this is the exact angle where it is toppling over and it is not. You might wonder for one thing is that for this experiment to work properly, there are a couple of things which are in play which are really important. You must essentially place this block onto the same surface or on the same location of the table for throughout your experiment, and that surface has to be horizontal. It cannot have the surface on which you are working. That surface should not be tilted in any side, because that way you will gonna have different values of turning effect. So having a spirit level to make sure that this bench is horizontal, first of all, is a pretty important step. And then we have to attach those mass. So once you get the maximum angle relevant mass, then you can slowly step down your mass by, let's say, decrements of 10 grams or 15 grams, depending on how much you can achieve, so that ultimately you can finish your experiment somewhere close to 0 degree. You can have 6 set of values. So that's something that I would go for, to find out the highest limit first and then slowly decreasing it, so that I do not run into the problem that that I might have to have attached too much mass, but the block is still not toppling. For example, let's say if I go for start from a very initial value and increment my angle by, let's say 10 degrees, and if you start from 10 degree, let's say 10, 20, 30, 40, 50, 60, 70. So even at the 70 degree, the angle will be pretty small. So the required amount of mass that you have to load onto this thing might actually become too large. And in that case, the strip will definitely bend, but the bending effect of the strip would not be too much of a trouble for us, but it can actually pose some trouble. What I want you to understand, if this strip bends significantly by the effect of the mass, then this point is going to get closer to the nail. Get this point, because this L that we are trying to measure from the nail to the hanging point of the mass, this is the actual length for the for the nail position and the mass position. If this strip actually bends a bit to the down, for example, if this strip becomes a bit bent, then there will be a bit of a curvature, and the distance from the nail to the end point P, that would become shortened. So that can lead us to some experimental errors, which we might have to take care about. As for measuring the W value, which is, I would highly recommend that we measure the W in multiple different places, locations of this of the wooden block, both on the top surface and on the bottom surface, and find out the average for the W. We also have to, what are the other variables that you have to find out? We have M, we have theta, and we have volume of the block has to be measured. So volume of the block can be measured by measuring the dimensions in all directions. Once again, we have to measure the dimensions in multiple places, find out the average to find out the average volume of the whole block. And then MW. What is this W? W is this dimension. Alpha is a constant, I believe. Alpha is a constant. Okay, fine. Design elaboration to such the relationship. Apart from these things, as for precautions, what I can think about is that because we are working with hanging mass and toppling of our experiment, there should be a sandbag or sand tray underneath the hanging mass so that it does not essentially hit the ground or makes too much of a trouble. Or there's you can mention a sand tray, you can mention a cushioning thing, you can mention a piece of foam that can be placed under the hanging mass so that whenever it's gonna fall, it's gonna be cushioned. We don't damage that part. I think that's pretty much it that I can think about. Yes, I'll take questions. Ashfia.
Sir, my question is, what does discrete increment mean in this scenario?
Step increase. That you have a fixed value. The next increment is a fixed amount. You cannot touch all the in between values. For example, let's say if you have 5 grams mass available to you, you can increase your mass by 5 gram each. So you cannot have any fraction in between. That's what discrete increment means.
Okay, and sir, why do we need to measure, I mean, how many readings do we have to take of W from the top edge, or we have to make the average? How many readings do we need to take?
Well, to be honest, the more the merrier. But in this case, I wouldn't go for that. For example, the W is basically this dimension. So I would say, let's say we have 4 faces over here for this object where we can measure the W. So this is a rectangular block. So I can take 2 measurements of each side so that I can have 8 readings. Then I can have the average of 8. 8. Do you understand how 8? So let's say you for this surface, this is the side view. You take 1 measurement along this line and then another measurement along this side. For that, and you do the same thing on the back reverse side as well. And as for the top view, you do 1 measurement along close to this edge and another measurement close to this edge, and you also do that for the bottom side as well. So there are 4 faces where you can measure the W. You take 2 readings each of from the surfaces so that you can get a total of 8 readings. That would be good. If you wonder why not 4 readings and measuring them from the center, because that is exactly what we are trying to avoid. We are trying to have an average value that can give us an average of the maximum and the minimum reading. So if there is a possibility that this rectangular block is not made exactly rectangularly, so there is some manufacturing error and some parts are more polished than the other. So measuring the dimensions on the side gives you a much more dependable averaging effect.
And sir, we have to use a sand tray. Instead of a sand tray, can I use something else?
Definitely, you can use anything that will cushion the falling of the mass. You can using a piece of foam. You can use a actual physical cushion. You can use you can use anything soft that will be able to hold that object, but essentially not get stick to it. For example, if you think that you can use a tray filled up with dry rice, that can also work. All that is important is that that falling mass shouldn't be toppling over and eventually get detached and eventually hit us and or roll over from the table. That's all that is. So you have to just cushion the falling.
Okay, thank you, sir.
Sure. Abiyaz.
Sir, I want to confirm one thing first. You want to change the mass and find theta from that, right?
I would appreciate that. Yes.
Okay, and another observation I made is that the maximum possible value of theta could be when P aligns with the corner of the block. That is something a bit weird to me. It's like theta cannot reach 90 ever, no matter how thin the block is.
Yes, true.
So can we mention that, like P, if P align the maximum length, the maximum possible value of theta will be that when P aligns with the corner of the block?
That's not essentially a very logical choice. I'll tell you what I'm trying to mean over here. What is the max? I mean, here's the deal. If you keep on attaching if you keep on attaching mass over here and keep on increasing the theta, up to a certain angle of theta, this block will have the tendency to topple to the right. Beyond a certain value of theta, this block will have the tendency to topple over on the top side, using this edge as the pivot line. So for our experiment, we are wanting this block to topple over to the right. So there exists a certain angle beyond which this block will not prefer to topple to the right, rather this will topple onto the upper side for this figure, or on the away side. If you are doing your experiment from here, this is a top view, this away side and closer side. So this block will tend to topple onto the other side. Exactly where that alignment of theta is located is actually dependent on a lot of factors. The first factor that is important is that how varied are these two dimensions. I mean, W and the length, how different are these two dimensions? I do not know an exact relationship that whether this angle theta would be actually relevant to the corner of this thing. I'm not essentially sure about that. I mean, for all I care, if this strip is really thin, then it might actually be possible for us to have this object toppled over, even if we are going beyond this thing. I'm not essentially sure where this maximum theta would be available. I cannot say it for sure. I don't know this. I might have to look up something, but what I can tell you from what you asked me is that there is definitely a specific point of rotation, a specific value of theta beyond which the block will not topple in the direction that we want it to topple. There is a maximum value of theta beyond which the experiment will not work.
But is it relevant to mention that, sir?
I'm not quite sure, but we can look at the Mars scheme. We can definitely look at the Mars scheme. Before I get into the Mars scheme, it is important that we have to work with this relationship over here so that it becomes a straight linear equation. We're trying to bring up a relation between m and theta. I have described theta as my dependent variable and m as my independent variable. So in this case, m is in two places. Okay, I'm gonna try and work with this equation. Just give me a moment. I cannot copy this, so snipping tool helps. So this equation goes like alpha VW equals to 2ml. Achha, you have to give appropriate ways to measure the L as well, which I did not mention, but I want you to think about it and come up with some ideas from your own conceptions.
স্যার এখানে কি আমরা থিটাটাকে ইন্ডিপেন্ডেন্ট বা
হ্যাঁ, শেষ করো, কোশ্চেনটা শেষ করো।
স্যার ইন্ডিপেন্ডেন্ট ভ্যারিয়েবল ধরতে পারবো থিটাটাকে নাকি ডিপেন্ডেন্ট?
Yes, we can consider either of them as independent and the other one dependent variable, but I would go for m as the independent and theta as the dependent. That's what I described. That why would I prefer that?
Okay, sir.
Sure. So I'm considering the m as the independent and theta as dependent. So if that is supposed to be true, so I have to bring up the L cos theta over on the other side and divide both sides by m. Okay. So let's bring the cos theta on the other side. So this would be 2ml cos theta equals to alpha VW plus MW. Divide both sides by m. And we can divide both sides by 2m actually. Or we can divide both sides by cos 2ml. Yeah, the whole thing.
So back to the first line, you can just factorize m from the right hand side.
Yes, I could, but I am not doing that because I do not know where it will eventually end up. If it's required, I'll do it in the last step. I could come on the m, but I want to make this cos theta individual. So I'm trying to get a y equals to mx plus c, that format. So the entire cos theta, I'm trying to make the cos theta itself free of everything and everything else on the other side. So this would give me alpha v w divided by 2ml plus mw divided by 2ml. Mm crosses out here. So this would be my mx plus c. So ultimately I should shift myself a little bit more. Like আস্তে আস্তে আকাশে চলে গেছে। So this should be a cos theta equals to, এখান থেকে যদি 1/m কে আলাদা করি তাহলে বাকি থাকবে কি আলফা p w divided by
2L.
2l into 1/m 1/m plus the by 2l. এই হচ্ছে আমার total equation. This is how I would go for. So I'm going to plot a graph of cos theta versus 1/m. This graph would give me a straight line with positive gradient which does not pass through the straight line. If that happens, then we can say the relationship is valid. The gradient equals to হচ্ছে এটা, এখান থেকে আলফাকে সাবজেক্ট করতে তোমাকে বলতে হয় যে আলফা ভ্যালু কিভাবে বের করবা। আর y ইন্টারসেপ্টে কোনো কাবজেক্ট মনে হয় আমাদের করা লাগবে না। কোশ্চেন according to the question we are only trying to find the value of alpha. Yes, that's all we're trying to get at. Can anyone else think of any other additional precaution for this experiment other than placing this whole thing under a sand tray? That's actually an additional detail that can be a precaution. We can also wear protective shoes. Goggles I don't think wouldn't be required because in this case there is nothing that can stick up to our eyes, but wearing protective shoes is pretty important because we are working with mass and moving mass. Yes,
I think goggles could be used because the strip, if it bends and you remove the mass, suddenly it could snap back and hit you in the eye.
yeah, true. We should also wear goggles. Yeah, we wear protective shoes and protective goggles so that mass doesn't fall on our feet. That you have to give the reason that why you have to give that protection. We use protective shoes so that the mass doesn't fall on our feet, and protective goggles so that if any times the strip breaks apart, it does not shoot to our eyes. Because it is possible that if you're doing this experiment without any pre-measurement, you might attach some too big of a mass and the strip is not able to hold that up. It breaks up and there is a possibility it might shoot to your eyes. So yeah, we should have both of them. Why not?
And sir, should we also make sure that the strip does not bend while the mass is attached?
Mentioning that would be a good idea, but you cannot avoid that, if you ask me. I mean, even if we use a metal strip over here just for the sake of better doing of the experiment, the strip will bend because it is working as a cantilever. Cantilever means it is being supported at one edge and you are applying load on the further end. So the strip will bend. For bigger masses, it will be bending more. For smaller masses, it will be bending less. But I believe that's the experimental hazard that we have to deal with. Either that, or the other thing that we can do, is we can have a meter rule attached by maybe a meter rule attached over here by a hanging no, that would be too much. That's not logical. It would bend. So you can say for one precaution is that we use a long enough, যত লম্বা নেব strip তত তারও bend হওয়ার probability আরো বেশি হবে. So what we can say is that we use a wooden block that is not too heavy and the W is significantly small, so that we have to use less amount of mass for the whole experiment, which will ultimately lead to less amount of bending of the strip. We can say that as an additional detail. That's one way to reduce the amount of bending, but you cannot altogether counter that, as far as I'm concerned. বুঝা গেছে?
Yes, sir.
Mark scheme to দেখি. Let's see what the mark scheme has to offer us. This is May June 1952. Are we at that? Yes, June 1952. So this is the thing. Okay. So first of all, we have this. Plot a graph of cos theta against 1/m or reverse. Acha, এখানে তো আর একটু আগে থেকে, sorry. M is the dependent variable, theta is the dependent variable, or vary m and measure theta, or theta is the dependent variable and m is the dependent variable. Okay, you can use them alternately. Keep position of the load constant or L constant. So in this case, they have considered L as a constant. If you ask me for control variable, I would go for one other thing is that we use the same block for all the readings, which is obvious, and also keep the L constant throughout the experiment. Method of data collection, label diagram, workable experiment, including load shown touching at P. How would you make sure that the load is touching at P? This is the part that I have explained in other cases, that in any case you are trying to hang an object, hang a load from an exact point at the end of a bar. It is always easier to do using a piece of string. So you attach the string inside with a piece of nail or a hole, something like that, and then you hang it with a mass hanger at the end, so that you can always apply the load exactly at that point. This always helps, and the beauty of hanging it by a string is that whenever the object, even if the object will bend, you would still have the application of the mass exactly on that label point. But if you and you don't have to bother about the masses toppling over or getting dislocated over the period. Just a second, আমি একটু বাকিগুলো দেখে নেই. Use a protector to measure theta. So they have only mentioned the use of a protector. I don't know why. Okay, they have done that. M is the independent variable. Slowly change the angle until the block just topples. Or theta is the independent variable. Slowly change the mass until the block just topples. Use a balance to measure the M. Okay, yeah, M এর to measure করা লাগবে. আমি এগুলো বলি নাই because I consider that these are given, that you have to have a way to measure all the variables of the equation with appropriate method. So M is to be measured, W has to be measured, L has to be measured, everything has to be measured with appropriate equipment that you have to mention. Method of analysis, blah 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 blah. So we are plotting this graph. It should value a straight line, not to the origin, unless the choice of the x is indicated in the intercept is 0. Acha. Alpha equals 12 by 12 gradient divided by VW, or alpha equals to this one. Acha. People can have different type of plotting. So if you plot cos theta versus 1 by m, you're gonna get this one, which we did. So alpha ultimate expression is beta. This is the correct expression for us. And then for the additional details, let's have a look. We use cushion or foam or sandbox in case the block or load falls. Measure L with a ruler. Okay. Why is this not a way of the method of data collection? Measuring the L is not a way of data collection. Okay, yeah, because L is not supposed to be your variable. Your variable is M and theta. So that's why they didn't mention the measuring of L in the method of data collection. Yeah, obviously it comes in the additional detail. Makes sense. Correctly position the protector to mass theta. Example, protector with center over the nail and the straight line edge to parallel to the edge of a block. Method to fix the M to strip. So this is the part where I told you for hanging the mass with a piece of string and a mass hanger. Method to determine the volume of the block. Example, V equals to W into H into L, which I said. Measure the WHL with calipers, some micrometer rules. So you have to mention the equipment over here, which I didn't mention. I mainly mentioned that you have to do it in multiple places and take the average for better results. But you have to mention the equipment as well as for the mass scheme. If M is the independent variable, repeat the experiment for theta and determine the average theta. Okay, yeah, this is something that I also didn't talk about because I take it for granted that if you whatever you are taking as your independent variable, you keep that constant and you've measured the dependent variable multiple times for the same value of the independent variable. So if you're taking your mass as the independent variable, you have to do the same toppling effect multiple times to get a more accurate value of theta by finding out the average of that value. So then it says that equation must be in the form of y equals to mx plus c with cos theta on one side and m on the other side. So exclusively cos theta should be free. That's what I meant, that because we are trying to, if you take theta as your independent variable, theta as your dependent variable, so cos theta should be on the left side and everything else should be on the right side. So that's what we did over here. So which worked for us. We get the exact same equation that is shown over here. Beautiful. Method to determine the center of the load or the center of the block. Example, measure diameter width or half the diagonals across the block. I did not mention that. Exactly at which point that nail should be nailed onto the wooden block, that should be a predefined factor, because you will not be having this apparatus ready for you. So you have to stick the nail onto the exact diagonal place, which would be vertically above the center of gravity of the whole block. So we have to find a way for this. This is actually pretty
এটা কি কোশ্চেনে মেনশন করা ছিল?
The question actually says that a student is investigating the stability of wooden block by resting on it. A strip is attached by a nail to the center of the top of the block and is able to rotate as shown in figure 1.1 or 1.2. That's all it says. But how do you place it up over here?
Just a diagonal intersection value.
Yeah. So then it says method to ensure that the block or strip is horizontal. Yeah, that's what I said. Check with the speed level. Yeah, that's what I said, that the surface on which we will be doing the experiment, that should be checked with the horizontal, the speed level for better working. And then comes question number 2. Yes, I'll take question. Abias, you raised your hand.
Sir, it says in the mark scheme about the protector for measuring theta, but your method of trigonometric thing, how would you do that, sir? Like finding the perpendicular distance of P from the 0 line.
And this is what I would do. For the exit toppling over value of the mass. So let's say we know the value of L because the value of L would be a constant throughout the experiment. So let's say we know the L. So this would be our hypotenuse. Let me take this image and I'll draw it onto the other part so that I can show you what I mean. Let me take this image. Okay, so we already know this value. Eta আমাদের already জানা আছে. So if you try to think about it, if you're trying to make a right angle triangle, a very logical choice would be to have a right angle triangle, assume a right angle triangle over here. Let me make it thinner and maybe with a different color. Okay, so you can have a right angle triangle right like this. So you can either measure L and you can measure this one. So that way you're going to go for the sine ratio, or you can measure this with the base. You can go for the cosine ratio. One way that I will be doing this is that if you want to measure the vertical side, we need to have a reference for this point and be able to hold it up over here.
A set square use করতে পারি.
We'll definitely use a set square, but I'm trying to think of how along what component should we hold the set square with. So we can actually do one thing. That is, we can place a meter rule right over here that gives us a reference for this line, and which should be clamped by some appropriate mechanism over here. So this would be hanging, let's say, 0.5 centimeter above the apparatus setup, and because our theta rule should never be 0, so you can have a meter rule right over here. Are you getting my point? So this is let me elaborate how I'm approaching this experiment. This block is placed over here. We have a clamp supported meter rule over here, and we should use the set square somewhere exactly over here. We can use the set square. Let me draw that with maybe blue. We can set the set square right over here to measure the exact value of that part, that how far apart is it from this point. The easier way to perform this measurement would be that first we find out that exactly for which angle the block topples over. First you do that without the presence of the set square or the meter rule, or they might be present there, but they are not going to be involved for your experiment. So we're going to measure for exactly, we're going to have a measure and determine for exactly what value of theta the block does topple over. That's the first thing we're going to go for. Secondly, we're going to get rid of the hanging masses and place this whole block right at this position without those masses, because if we don't have those masses, the theta would be perfectly represented, whereas the block would not be toppling over. So you would have a stationary apparatus setup to go and measure this theta more accurately. So then you can have this measurement as well.
Sir.
Yes.
Could we do like from the nail to the set square, then we get cos theta directly?
So you're saying, yeah. If you have a meter rule over here, your choice can be anything. If you place a meter rule over here, if I place a meter rule over here, we can directly go for this one and this one. We can directly calculate the cos theta. Yes, be my guest. Yeah, sure. Or if you don't have a meter rule over here, if you have only another wooden strip just to support this reference line, then you might actually have to find out cos sin theta, and the measure from sin theta you can go for cos theta. It works either way. Yes, yes, definitely.
Yes, sir.
Sure. Ashvia.
Sir, in point number in mark schemes, one of the points it is said that how to keep the strip horizontal. It said that we have to use spirit level, but instead of spirit level, can I say that in any other way I can keep the strip horizontal?
To keep a certain object horizontal, I mean, if I use the term horizontal, it means horizontal with respect to Earth's gravitational field. I mean, in the bigger sense, Earth's gravitational field means, let's say, the gravitational field lines are coming, are entering this, entering the ground vertically, and being something horizontal means that is perpendicular with those lines. So a spirit level, it typically serves the best mechanism that by which you can check the horizontality of a certain equipment. If you don't want to consider this as a horizontal, rather if you consider the other version, that if you consider will be only parallel, then you can also say that we can try to make the strip parallel with the table by measuring the strip in multiple places with the table. For example, what I mean is that we can try and measure the height of the wooden strip, let's say along this place and maybe along this place in two different places, to make sure that it is exactly equal. This will essentially make sure that this strip is parallel with the table, but that doesn't ensure that the strip is horizontal. To check horizontal, spirit level is always the most commonly used and more what can I say, accurate equipment to use.
If we have to use spirit level, because if we measure that parallel way, then we also might have parallax error. That is why we use spirit level.
Precisely. Okay, I think this question is done. I think last class we did mark some other question that I would like to discuss this class, right? Did I? যে নেক্সট ক্লাসে এটা আলাপ করব বা এই ধরনের কিছু?
স্যার ওই যে মেজন 18 এর একটা কোশ্চেন ছিল, বলছিলেন যে উইয়ার্ড কিন্তু কোশ্চেনটা ভালো।
মেজন 18 এর?
হ্যাঁ
দা দেখছে। বসো, বুঝতে পারে না, বসে থাকো। This one.
হ্যাঁ স্যার এটা।
Yep. Before I jump into the question on my own, I want every one of you to read this question and generate some ideas. I want you to think, first of all, how to have this equipment in a way so that it is actually stable and we can actually take measurements out of them. Try to think about that first. কোশ্চেন কি বুঝা যাচ্ছে?
Sir, how are these arranged in space? Is it like top and bottom, or
Yeah, definitely top and bottom, as the question says. How would you arrange these two things to be located in physical space in a stable arrangement so that you can actually be able to measure that R?
sir, let T hang from somewhere and let S sit on the top and balance?
Okay, and then how you make sure that they are perfectly perpendicular to each other?
Put them in a
স্যার
sl-
একটা
Or can we use a cardboard to ensure that they're in the same plane?
Cardboard aligned how?
Vertically, or এটা clamp করে রাখতে পারি.
put them in a cylinder, sir.
We have to have a cardboard in all sides then, at least on
স্যার
4 sides.
একটা হলো সিলিন্ডারের ভিতরে দুটো ঢুকাই দিলে হয়?
That is a logical way. We can use
Yeah,
a
that's what I was.
hollow cylinder. But one problem with the hollow cylinder would be that I mean, actually, we do not need a hollow cylinder per se. When I first came across this problem, the only solution that I could think of is a transparent hollow cylinder, because I was thinking that one thing, I was assuming that this object, this metal sphere T, should be floating above the metal sphere S because of the repulsion. That's what I thought. Then I eventually came across the Mars scheme, and then I come to understand that that would be highly difficult to achieve, because to counterbalance the weight between two metal spheres, I'm talking about metal spheres here, you'd require some huge amount of voltage to create a significantly high amount of repulsion. That is actually quite difficult to achieve. So one logical way is that we can hang the T sphere from a stationary point with a string, or you can essentially clamp it as well with non-metallic clamps. That's pretty important, because if you do it with metallic clamps, you're gonna have the charge discharge. So you can either clamp it or you can hang it, and then, I mean, having it hanged can give you a bit of a trouble, that whenever you produce the repulsion, that mass can actually slide a little bit left or right. It can move a little bit left or right. You can come across a bit of a variation of force. But if you clamp it all together, then you can very easily measure the distance, because having it clamped, it will not move at all. That's the beauty. And also the force can be a fixed value, because if these two spheres don't move with respect to each other, then the magnitude of the electrostatic repulsion force that you'll be measuring out of the top and balance would have a fixed value. So it would be easier for you to take readings. So I would go for clamping the sphere T above the sphere S with a non-metallic clamp. That would be my preferred choice of method. Point one. How do I place both of them perfectly vertically on top of each other? That can be arranged very easily with a set square and a meter rule. If you wonder how is that possible, let me show you a possible way. Or you can have a big enough set square, or you can have just a rectangular piece of cardboard. I think something that Rafid proposed that can work as well. I should take that picture. Kuyalo. So one of the things that we can do is that how would my figure, my apparatus setup could look like? I'm gonna get rid of this figure 1.1. Let's get rid of that. First of all, I'm gonna place sphere S on a top end balance. But if I only place the sphere S, which is a spherical object, on the top end balance, there is all possibility that whenever I'll give them the charge by touching them with a positive lead of a something, then this is gonna start to roll around. So other than having it allowing to roll around, I'm gonna use cylindrical seating arrangement. For example, let's say the cylinder of a tape, Scotch tape, you know. So you can place some spacer. Where is that? Rectangle. Okay, yeah. You can place some spacer over here on which this thing is gonna be sitting on the top end balance. So you're gonna have that. It's gonna sit on that, and then you'll place your top end balance underneath that. So let's say this is gonna be my top end balance. You just label it as top end balance. It's a rectangle. It perfectly works. You don't have to show digital reading or anything. And then to make sure that these two things are perfectly on top of each other, we can use a plumb line. Actually, using a plumb line would be a better idea, I think. Do you guys know what is a plumb line?
A string with mass at the end.
Plumb line এর একটা ভার্সন তোমাদেরকে দেখাই।
Sir,
Yes. Yes, মুগ্ধ বলো। Hello.
স্যার আপনার এই ডেস্কটপের ওয়ালপেপারটা কি বারবার চেঞ্জ হয়?
এইটা
জি স্যার।
এটা ডেস্কটপ না, এটা ব্রাউজার।
জি হ্যাঁ স্যার, চেঞ্জ হয়?
হ্যাঁ, এটা অটোমেটিক্যালি মাইক্রোসফট এজ এর সার্ভার থেকে চেঞ্জ হয়। They do this. I don't do this. It's nice, right?
Yes sir.
Woodworking plumb line. Actually woodworking এটা masonry plumb line হবে। I was looking for
Acha, sir, can we use a single retort stand and two clamps so to ensure that they are over one another?
We can, but how would you make sure that the length of the clamps are exactly precisely same distance from the block? Because we are talking about spherical objects, so taking measurement of the center can prove to be slightly difficult. There can be a lot of different ways to achieve this. হ্যাঁ বলো বলো মুগ্ধ বলো।
But we are using identical spheres, right? As in for charging them.
Yes.
So if we use bosses of equal length and clamp them, I think they will align with each other.
They can, but I'm talking about very precise amount of gaps that you can have, let's say within the fraction of a centimeter or within millimeter scale, not fraction of a millimeter, within millimeter scale. You can have a little bit of distortion between them. What you're proposing can essentially work if all of our equipments are perfectly identical. But having identical equipments available in lab can prove to be a bit difficult. Wouldn't you agree?
Yes, sir.
So I'm proposing a solution. This is not the only solution, but this is just one solution that just popped in my head right now. This is how woodworking, masonry plumb line looks like. This is one of very common example. What is important for this thing to work is that the diameter of this cone is exactly equal to the width of this block. For example, in this case, you can see this person is holding this thing over here. So this is basically a plumb line, but the distance from the string to the card border is exactly equal to the width of this thing. Or in other place, if I can show you, if there is another figure, something like this. So this gap from the hole to the side is exactly equal to the diameter. What the advantage of this thing is that you can essentially have two things, I mean, perfectly aligned to each other whenever they're only touching each other. So one of the ways that we can do is that you don't essentially have to explain this in a very wide concept, but I'm showing you this detailed view so that you can actually picture it in your head, so that you can go ahead and write about this. We can use a plumb line to make sure that these two things are perfectly one on top of each other, even they're pretty much far apart. So we can place that rectangular block over here, and this hanging Latin thing, this cone thing, that top shape thing, that can be placed over here, and we can essentially measure that that they are equal distance apart. And you can do this in all orientations and on all sides, as many as you want. Actually, measuring it in 4 different sides is good enough, or 3 different sides is also good enough. So you can measure it in 3 or 4 different sides, as long as you can have that they're all both perfectly aligned. You can essentially make sure they're perfectly vertical to each other. This is pretty important. And then to make sure to measure the distance between these two things, we can go for one important thing is that we're gonna place it over here. আচ্ছা না yeah মুগ্ধ তুমি তুমি একটা জিনিস প্রপোজ করছো যে we're gonna clamp both of them by the clamps. That's not going to
Yes,
be allowed,
sir.
because we have to place the lower one on top of his top and balance. If we clamp the lower one, you're not going to be able to measure the variation of force. The top one can be clamped or hang by a thread, but the bottom one has to be sitting onto the top and balance, and that's it. You can clamp both of them.
Yes, sir. Got it, sir. Thank you, sir.
Sure, no problem. So that's one way we can achieve this. And another thing is that to be able to measure the in between distance properly, what I would like to does the question say that they're identical? No. The student is investigating the force between the two charge metaspheres S and T. That's all they say. So they might as well be not identical. Yeah, beautiful. So what we can do is that we can measure their individual diameters before we start the experiment and find out the individual radius. And then while we're taking one set of reading, we can measure their in-between gap by the help of a set square. That can be very easily achievable. Do you understand how? Hold on. Hello?
I'm not sure.
Let me show you. Let's say this is your table. Okay, this is a table surface, and you can hold up a vertical meter rule over here. Let's say just like that. You have to show essentially stand and clamp over here, which is really important. And then you can have a set square. I have to draw a set square and then rotate it. I will need a bit more width, I believe. So transparent selection. Okay, we can use one over here to find out the possible position of this one's bottom, and then rotate this, find out the second position over here. So you find out the in-between gap of them, and then add the individual radius with that measurement to find out the distance between them. That's one way to do. Another thing that can be done is that once you fix up the object perfectly in the clamps, you can actually label the halfway point by some marker, and you can measure the distance between those 2 points. I mean, let's say you give one mark over here, you give another mark over here. Every single time you'll measure the gap between those 2 marks. That is also a way, but in my way, it's not very precise. I would definitely, if I was doing this experiment, I would go for this one. I'd measure the diameter of this thing in multiple different orientations, find out the average diameter. I'll go for this one and do the same thing, calculate the radius. I'll know the individual radiuses. Then I'll measure the in-between gaps with the help of a meter rule and a set square for a certain apparatus setup, and then we'll measure that value. এখানে আমি already experimental setup নিয়ে আলাপ করতেছি. What is one thing that I actually skipped, which I shouldn't have had, is to find out which one is the dependent, which is the independent variable. Read the question. Each sphere may be charged by connecting the positive lead from a power supply to the sphere and then removing the lead. The electromotive force EMF of the power supply used to charge the sphere T is V. So we are going to, each sphere may be charged by connecting positive from the power supply to the sphere and removing the lead. The electromotive force EMF of the power supply used to charge sphere T is V. Okay, so we have charged sphere T in V voltage. The force between two charged spheres may be determined by the sphere to by top and balance. For a constant charge on sphere S, it is such that the relative Fujian force F and V Is it? Okay. So so what I need you to understand that, have a look. We are going to change the voltage which charges the sphere T from a variable power supply, because V is the variable here. And we are going to have a fixed amount of charge on a sphere S. So sphere S is not going to have any variation of charge. The only variation of charge is going to be implied upon sphere T. And we are not going to know how much charge we are working, but we're going to know easily from how much voltage supply are we going to provide this charge. What that circuit is going to look like, I'm going to show that to you. Don't worry about that. I'm going to show you that circuit. Don't worry about that. So, yes.
স্যার সিএস কোডটা দিয়ে করলেন বুঝলাম না, ওই যে ইনবিটুইন ডিসটেন্সে মাপলেন যে
কিভাবে করছি? I'm going to find out this point. Let's say, আচ্ছা, সেট স্কোয়ারটা আগে ছিল হচ্ছে এরকম। সো আচ্ছা, রেডিয়াস বের করার পার্টটা তো বুঝছো?
হ্যাঁ হ্যাঁ
অ্যালাইনমেন্টের পার্টটা তো বুঝছো?
হ্যাঁ।
Acha. So I'm going to put the set square right up over here, placed with a vertical meter rule. This meter rule will be clamped, and I'm going to find out this exact position on the meter rule, a position.
আচ্ছা।
And then I'm going to rotate the rotate this thing, rotate the set square, and then I'm going to find out this position as well on the meter rule. So this will give me the exact distance from the top and the bottom of the two spheres. Then I'm going to add the individual radius. এটার radius add করব তার সাথে, এটা radius add করব. So by adding up all of those three readings, radius of top sphere plus in between gap plus radius of the bottom sphere, together gives you the value of R. That can work.
Yes sir, understood. Thank you sir.
No problem. আচ্ছা, এখানে so we are going to have sphere S charged at a fixed amount of charge. So that should be provided from a fixed supply once and shouldn't be changed over the duration of the experiment. And we have to make sure very carefully that this sphere S is not discharged at any way. Even when you are checking for your alignment and everything. I mean, you should check your alignment and your measurement apparatus, everything first, and much later should you start doing the experiment. And for the whole experiment performance, I would highly recommend that we wear rubber gloves so that we do not accidentally discharge the spheres at any way. All the equipments which is touching the spheres should be insulated or made up with non-metallic substances. You can say plastic specifically, no problem. So these are some additional detail or precautions that I'm talking about, which can eventually pay off in the long run. Okay, Sam. You can pay off in the long run. So the other thing that is pretty important, so here we have to place the surface S, sphere S at a fixed voltage, and then we have to change this sphere of the charge sphere T. The question says that for a constant charge on sphere S, it is such that the relation between F and V is this much. So R will not be a variable. Throughout the experiment, R will be fixed. What we are trying to define a relationship between the voltage V, which is the voltage by which we are going to charge up this sphere T, and we are going to be and the force by which they repel each other. So R will not change. So you set up the whole apparatus once, you don't have to change the R anymore. You set up the alignment once, you don't have to change the apparatus setup anymore. All that you have to do is you need to have a workable circuit. Let me show you the possible workable circuit for this question. What comes into my mind. We can have a circuit that looks like this. আচ্ছা, আমি পাশেই আঁকি। মনে করো হচ্ছে, let's say we have a DC supply. Let's say we have a DC supply. এই DC supply একটা ফিক্সড ভ্যালু আছে। মনে করো এই DC supply হচ্ছে 20 ভোল্ট। And fixed voltage দিয়ে আমাদের কাজ হবে না। We would have to, আচ্ছা, এই কোশ্চেনের ইন্ডিপেন্ডেন্ট ভ্যারিয়েবল হচ্ছে ভোল্টেজ, ডিপেন্ডেন্ট ভ্যারিয়েবল হচ্ছে F. We're going to change the voltage by which we're going to charge up the sphere T, and we're going to measure the force from the top and balance. এটা কেমনে করব সেটা আমি বলতেছি। Yes, ফাহিম কি সেটা বলতে নিছিলা?
জি স্যার, ওই যে আমরা যে যখন এই সেট স্কয়ার দিয়ে যে আমরা মাপলাম ডিসটেন্স, আমরা মানে লিখবোটা কিভাবে, মানে ওয়ার্ডস এ একটু ডিফিকাল্ট হয়ে যায় না?
I think 3 sentences will suffice. What I'm going to write, what I propose that I will write that we measure the diameter of both the spheres in multiple orientations and find out the average and calculate the radius. Using a vertical meter rule and a set square, we measure the distance between the two spheres. Then adding the distance with the two radius gives us the R.
তো এইটুক বললে হবে।
এটুকু বললেই হবে।
ওকে, আচ্ছা স্যার।
Sure. X second. Hold on, তোমরা এয়ার সাপ্লাই গান শুনো? Anyone? Anyone? Air supply? Maybe not.
স্যার একবার
They make pretty good music. Anyway, let's say we have a DC supply which is 20 volt. A fixed 20 volt supply wouldn't be good for us. We would like this to work a bigger voltage. এখানে important part হচ্ছে I would appreciate sphere S to be charged at a pretty high amount of voltage because I'm not going to be changing this over the time, so that my measured force value would be pretty high. The way, in my opinion, this circuit can work is that we'll definitely have a switch. We'll definitely have a switch for functioning, and we can have a variable resistor. One of the side will be connected to the ground. The other side will be our touching lead, and we can have a voltmeter. এটা তো একটু ঝামেলা হয়ে গেল। Actually, we can have a fixed resistor over here. And have the voltmeter connected across. সার্কিটটি কাজ করবে বলো, দেখো তো। আচ্ছা, আমি একটু সুন্দর করে রাখি। So what I want to have a workable circuit that can, for which I can measure the voltage before I do the connection, and something that can also do me the purpose. Now, for me, for the circuit to give me, I will be only touching the positive end of the supply to the sphere. So the negative end has to be connected somewhere, because the battery would only give out charge if it receives and give out equal amount of electrons. That's where the ground comes in. So if it's a 20 volt supply, and then you have a switch, you have a variable resistor to change the output voltage, and let's say one end is connected to the ground, negative end is connected to the ground, you can essentially use this point to have it voltage, have it connected to over here. But you cannot have a very specific, but how would you measure this voltage? Now the problem is that you can think about connecting a voltmeter across these two ends over here to measure this voltage. Well, you do understand, whenever we have connected the negative end with the ground, this end will essentially become 0 volt, this end will become 0 volt, and this positive end will become plus 20 volt. So this perfectly serves our purpose. But so currently this will work as a 20 volt supply, no problem there. But whenever you will have this thing, if you want to, if I now connect this with any of the sphere, they'll be charged with the voltage of 20 volts. But how do you vary this? To be able to vary this, you would require a mechanism so that this endpoint voltage can be changed. This variable resistor cannot essentially do that, because this variable resistor is not connected with anything. So one logical way that I can think of can be like this. Other than having the voltmeter connected all the way right over here, having it connected all the way over here, we can have a fixed resistor over here, and the voltmeter comes a bit later. Voltmeter একটু পরে দেখাচ্ছি। You have to show the workable circuit for this whole thing to work. Other than that, you will be losing mark. And now, think about it. Now, whenever I'll close the switch, this circuit will work. ঠিক না? Kids.
Yes, sir.
If I now close the switch, have a look. This circuit will definitely work. because it's connected to the ground and everything. This is working, having it connected to the ground, making it 0 volt, which perfectly works, and the voltage will be shared between these two things. If you take out a connection point out of it, this connection point will give you the voltage that is the remaining voltage after the variable resistor has eaten up. So this will be the exit voltage that is used up by this fixed resistor. So you can essentially connect a voltmeter right up over here to give the exact voltage value of this point. Think about it. এই সার্কিটে বুঝা যাচ্ছে সবার?
Sir, can you repeat?
We are trying to having a open positive end connection, which should be able to give us a variable positive voltage output that we should be able to measure with a voltmeter as well before you connect it to the sphere. So to have it changed, I attached a variable resistor. To be able to measure the voltage before I touch the sphere with, I connected this fixed resistor. So what is going to happen? Whenever the switch will be closed, let's say this switch is currently closed, the current will flow through this in this direction, conventional current, and the voltage will be shared between these two resistors. If let's say this is 20 volt, let's say that the supply is 20 volt, so the value of the positive end is plus 20 volt right now. If this resistor is, let's say 5 ohm, and this resistor is, let's say 5 and 20 সাথে আর কিসের রেশিও হয়? Okay, let's say না ওই উপরটা 5 না, let's say if this resistor is now 2 ohm and this resistor is 3 ohm, then the voltage will be shared in 2:3 ratio, which means this will be using 2/5 of the 20 volt. 2/5 of the 20 volt means how much? 2/5 into 20 means 8 volt, তাই না? So out of the 20 volt positive 20 volt supply, this variable resistor will be eating up or using up 8 volts, and this will be using up 12 volts. So the exact voltage value of this output point would be plus 12 volt at this moment. A valueta exactly a voltmeter read করতে পারবে, because this voltmeter is trying to read off from this point all the way to the ground. So this will be able to read off perfectly 12 volts. So before you connect this into one of the spheres, you can have a measurement of this point's voltage by using this voltmeter. That's how I meant.
Okay, sir, understood.
Abes bolo.
Sir, this is pretty elaborate, but I've seen like variable DC supplies and stuff. Why not use those?
You can use a variable DC supply. Works. You can connect a voltmeter across the variable DC supply, connect one end to the ground, and use the other end. Beautiful. I did not use that shortcut version because I wanted to show you that exactly how this can work with a fixed supply. The variable DC supply can work even much too easily. For example, let's say you draw up a supply, plus and minus. You give an arrow in between. This thing makes it a variable DC supply. This arrow over here means this supply voltage can be changed, which is basically how we can work with our rectangular power supply boxes that I have in my laboratory. Many of you have worked with, or in other laboratories as well. So we can simply have a switch. We should always have a switch. And we can simply connect one end to the ground. And we can simply connect a voltmeter with this thing. This supply would just work as fine. So what is inside this variable DC supply is basically this whole thing. I wanted to elaborate the content of the variable DC supply to make sense to you. It's not essential that you have to draw all of this. You can also draw only this much. This is working as a variable DC supply, a switch, a voltmeter connected across these 2 points. This voltmeter gives us the output voltage, and this works just fine.
I see, sir. So would this fall under vague computer methods or?
No. No, this will not fall under a computer method, because you actually have available in your laboratory those power boxes which can give you a variable voltage output. You can have a variable voltage all the way from 0 volt to 20 volt output from those boxes, so that those boxes can work as a variable voltage output. You have that component available in your laboratory, so this is not a vague computer method. And you can have a measurement of that voltage by using that voltmeter. Okay. Abdul Rahman made a question. Why is an earthing in the circuit necessary? Here's the deal. any battery or any variable, any DC source always works in such a way that it will give out some current if both the ends have a way to exchange electrons. A battery at any given time will always have the same number of electrons within itself. If you connect a battery to anything, for example, let me show you. Let's say this is a battery. It has voltage difference across it. If I now connect a bulb over here, just like that, this bulb will not glow because there is no way the current can happen continuously. If I now connect this end all the way up to here, now the current can flow and the bulb will glow. That way the battery will drain. But the way the battery will drain, that any single time, all the number of electrons that it will receive from this direction in the positive plate, the equal number of electrons will be leaving from this end. So you have to give the battery or DC supply a way for it to accept and give up equal number of electrons. That's where the ground comes in essential. Because if I don't have the ground, then I cannot have it a perfectly positive potential. Connecting the negative end with the ground, I'm making sure that this negative terminal is becoming absolutely 0 volt, so that the positive terminal is at the absolute positive value of the voltage supply. So if this is a 20 volt supply, this fixed end over here is working as a plus 20 volt supply. I can make sure that this is plus 20 volt because as per the question, I was instructed to connect it to the positive voltage supply. So if this is plus 20, I can make sure this is plus 20 volt supply only by connecting the negative end with the ground. That's why the earthing is necessary, to making for making sure that the positive end is absolutely positive. বুঝতে পারছি? Okay. So what we're gonna do, we're gonna first set this thing to the maximum positive voltage and connect this thing with the sphere S and have a fixed amount of charge in the sphere S, and we're not going to change this over the whole duration of the time. Let me go a bit more elaborate on how we're gonna set this experiment. We're gonna set everything up. We're gonna measure all the distances. We're gonna keep them aligned and everything. We're gonna place this whole thing over here. The top end balance should give us some reading, which is gonna be the total mass of the sphere, this placement mechanism, a hollow cylindrical structure, tape or something. So the top end balance should give us this reading. What we can do, we can now place that tear button. Every top end balance has a tear button. Tear basically means it's a sort of a reset. If you place that, then the topless balance will give you 0. It means it will read all the weight or mass on top of it as a balanced load. It will measure all the load above that. That's one way to do this thing. You can place the tear. That way, whenever there will be a force variation, this will read that force variation. Or if you don't want to use that tear, you can say that we record the reading of the top end balance, and then as we'll do the experiment, the reading will increase, and the subtraction of those readings gives us the value of F. You can go by either of them. And what is important is that top end balance should be placed in Newton value if you directly want to get the force out of the top end balance. So either you place the unit of the top end balance in Newton, or if it is placed in gram, then or kg, you have to find out the force using W equals to mg. You have to mention that. Either you have to mention about the scale setting of the top end balance, or you have to mention that whatever the mass value that the top end balance gives us, you have to convert that into force by W goes to m into g, where g goes to 10 meter per second square. You have to mention that so that we can have a proper measurement of the F value, because we are trying to find out the relation between force and the voltage. Voltage can be measured out of the voltmeter that I just showed, and the force has to be defined in a practical, achievable way so that you can have a proper way to measure that up as well. So that's what that comes in. So we are going to touch the S sphere with the positive end of the supply, or with that connection point first, and then we're not going to do anything with the S. Then we're going to touch the T sphere with different value of voltages. So how many voltages, how many voltage values should we have from the supply? We can predefine those values. For example, if it's a 20 volt supply, you can go from, let's say, I'm not going to have a very small amount of voltage difference because I would like to have a pretty high value of force. So I might as well go from, let's say, 10, 12, 10, 12, 14, 16, 18, 20. That can work for me, 6 set of values. Or you can start from 8 if you have more. But it is better to reside more on the higher side of your voltage rather than more on the lower side of your voltage to have a significantly strong force so that your top end balance can actually measure and give you a measurable reading out of it. If you have a smaller force, then if you have a small voltage on your sphere T, then the charge would not be as much on sphere T, so that the amount measure of force can be too small so that your reading might not be very accurate. So residing on the upper side of the voltage end is a much better choice compared to resetting on the lower end of the voltage end. That's what I'm trying to mean here. So I'm going to attach those and I'm going to measure those voltage. If you wondered that how can we do repeat and average for these readings, there is one way to repeat and average. The repeat and average way can go like this. Kids, listen to me. First of all, we're going to do the whole apparatus setup, and then we're going to connect then we are going to charge this sphere with the highest voltage amount. Then let's say we're going to start from the highest and gonna go backwards. So we're going to touch this sphere with the highest amount of voltage, this end of the battery. So this can be simply a head of the crocodile clip, which is essentially that crocodile clip can be just an open crocodile clip. So taking a connection from here to the open end, and you are wearing rubber gloves so that you do not discharge the spheres by accident. So what we're going to do is that we're going to touch this metal end of the crocodile clip over here and allow the top and balance reading to come to stable, and we're going to take this reading. This is going to be our first reading. To make a repetition of the reading, we'll have to first discharge this sphere. We'll have to discharge this sphere, connecting with the earth connection, so that this reading will become 0. Whenever this reading becomes 0, it means there is no repulsion between them. And then you do the whole thing once again. And if it's the same reading, you record the same reading. If it's a bit different, you also record a bit different. So you can repeat the same reading for the same amount of voltage by which the sphere T is charged by. You can repeat that reading, but to be able to do that every single time, you have to first discharge the sphere T and then recharge the sphere T once again by using the same voltage. So you're going to record the voltage from the voltmeter, measure the force value from the top end balance. These are your two recording mechanisms, and this is how you can do multiple readings, and eventually you will have a 6 set of reading. What is the equation in our question? The equation gives us that f is proportional equals to alpha v square v divided by r square. V in this case is our independent variable, f is the dependent variable, so the equation is pretty much already arranged for us. So you don't have to do any more arrangement. All that you have to say that we're going to plot a graph of force versus voltage. If this is a graph, this is a straight line with positive gradient that passes through the origin, we can say the relationship is valid. Gradient equals to alpha by r square. ওখান থেকে আমরা alpha by করতে পারবো. If you wonder for precaution of this experiment, already I have said that one of the primary precaution for this experiment is to have wearing rubber gloves so that we don't get any problem. And we're going to work with bare ends of the circuit. So the circuit should not be turned on for significantly long amount of time because that can lead to heating of the wire. Overheating might give us some shock as well, might give us some problem. So we should be careful about that. But between taking every reading, we should take some gap, and the circuit should be kept turned on for the least amount of time possible to avoid heating effect. This is also a logical precaution for the experiment. So overheating of the circuit ends could be one precaution. Wearing rubber gloves is a very, very good precaution, and taking some time gap in between readings to allow the circuit components to cool down is also another good precaution. I think I've covered pretty much everything. Can you guys, anyone think of something else? বললাম তোমরা কি বুঝছো এক্সপেরিমেন্টটা কেন ইউনিক?
Sir, can we say about the set square?
How we are going to measure the value of the R is going to be an by default additional detail for how to measure the R properly. So they're going to say in the mark scheme, I believe, is that in the additional that there should be a logical way for how to measure the R properly. So either by marking on the spheres, measuring that gap in between, or you can go for the method that I just said, that measuring the radius and everything. Yeah, that also comes in. That will be an additional detail, but I cannot think of it as a precaution, I think. Let's have a look at the mark scheme, maybe. May-June 1851. অনেকখানি উপরে উঠতে হবে। আর একটু পরে। There were. Which is the independent variable? If it's the dependent variable or variable measure f, keep r constant. Obviously, label diagram for a workable experiment using T suspended clamp or ceiling, S on top and balance vertically below T, T and S label at least or and at least one other label. So at least one other label means that you have to pretty much draw the same thing, and then you have to label at least another thing. For example, the meter rule, stand, clamp, or if you will have stand clamps supporting this thing as well. You can label a set square, you can label the top and balance this rectangle, you can label this one seating mechanism or hollow cylinder. That also works to make sure that it doesn't roll over the top and balance. Okay, so you have to have both of those labels and also at least one another label to make sure that's okay. If equals to difference or change in balance readings when sphere is uncharged and charged. Spheres or sphere S. What? S is the bottom one and S is the top one. Which one is what?
This is the bottom one, sir.
S is the bottom one. Okay, whatever. Maybe they are proposing that we're gonna have this thing for a constant charge. I'm not sure why they mentioned S over here. They should have mentioned T over here. Anyway, F is the difference between the two readings, between whenever any of them is uncharged. I mean, you don't have to have both of them uncharged. If any of them is uncharged, you have zero force. Electricity repulsion. Voltmeter across a power supply with flying lead, or read from high voltage supply, or EHT power supply. EHT power supplies are actually meant as extra high tension power supply. I can actually look up this word just to make sense since it shows up. Why not? EHT cycles are fully floating so that the certain relation of positive and negative terminal may be safely connected to Earth. EHT outputs are taken from a 4mm shorted package where EHT power supply. What does it mean? Extra high tension. Okay, yeah, exactly. But that means nothing to me. Typical values for this means these are some variable voltage supplies which have flying leads out of them. They're very high voltage but very small current, so you can touch them, but you're not going to get a shock. But they can work for static electricity scenarios like the way that we have explained. Yeah, if we had tried to find out a look for these things, yeah, this sort of stuffs. Here they are trying to produce some extra high tension of high voltage between them, so that they might see some ionization in between because of the heating of the candle. This is a pretty nice experiment actually. High voltage doesn't look like this. This is basically ionization of the air molecules, but which is a basic outcome of high voltage difference. You guys do understand that sparks produced in the atmosphere are basically ionization of the air molecules. Do you guys understand that? Hello?
Yes, sir.
That whenever sparks are produced in the atmosphere by a extra high tension or the lightning, these are basically momentary ionization of the atmospheric molecules, which make them glow momentarily, which makes this pathway. Because to give out light, to give out photons, something has to glow. What is it that is glowing here? It is those atmospheric molecules.
Gas particles.
Why are those glowing?
Plasmas.
Yeah,
Plasmas.
exactly. They are plasma. Should I say plasma?
Electrons go to a high energy state, release electromagnetic radiation, sir.
Exactly. That's what I meant. I'm not going to essentially go for the idea of plasma. It might as well be plasma. I'm not very sure about this, but plasma actually means that your entire atomic structure is destroyed. So you have a hodgepodge of free electrons and nucleus. So you have nothing else. So that can be a bit difficult for me to explain or visualize even. But what I'm sure that we have ionization of atoms over here. So electrons are jumping to higher level and lower level, and they are emitting those photons, which are making them to give this glow. So yeah. Anyway, there I moved here from the idea of EHT supply. So you can also have EHT supply. If someone thinks about this thing, that is also apparently acceptable, because this is a laboratory equipment that might be found, not very common in my opinion, in at least in the laboratories that we have. Measure R with a rule. That's it. Good. Method of analysis: plot a graph of F against V, allow log graphs, addition valid if a straight line passes through the origin is produced. You see, now they have mentioned that it has to pass through the origin. So that's why I always say that you always mention the type of the gradient that you're expecting, positive or negative. You mention that whether this line should go through the origin or should not go through the origin. Mention the give the entire detail of the expected straight line that you are plotting. This is always good and great. Examiners, you are usually pleased when they say this level of detail in the student's answer, which makes a good impression. Alpha goes to get into R square, constitution of the graph, and then comes the additional detail. Safety precaution linked to avoiding shock or high voltage insulating gloves, or whole flying lead to charge sphere to avoid electrocution. Use shrouded leads to ensure that there are no bare connections or avoid touching metal parts. Okay. Use of insulator between sphere S and balance, or use of insulator between sphere S and balance, or between T and stand. Oh, acha. I actually mentioned both of them, that we have to have some, what this point is that we have to have plastic holder for the sphere T. The clamp should be made of plastic, or there should be, it should be, the clamp should be insulated. And also between the top end balance and the surface, there should be a spacer, insulated spacer, so that it does not lose its charge. These additional details they have mentioned over here, in my opinion, they are actually quite mandatory for the system to even work out. Because if you miss out on any of these, your whole experiment will not work out. You're not going to get any force value, because if you're continuously losing the charge from any of these spheres, either the top one or the bottom one, your force will not exist, period. So although they're giving additional details, in my opinion, they are mandatory for the experiment to work out. Discharge spheres by earthing or cutting to the negative power supply. Additional detail to determine example radius of each sphere and add the distance between the spheres. That's what I said. Or measure from the top of the S to the top of the T. You see, this is the point that I'm trying to get at. If you measure from top of the bottom to, if here's the deal, measure from the top of S to top of T. I was about to say that, and to be able to say that, I have to have the information that these two spheres are identical. Nowhere in this question does it say that the spheres are identical. Have a look. Do you see it anywhere? Anyone?
No.
So if these two spheres were identical, we could have measured from top to top, and that would be R, or from bottom to bottom, that would also be R. Works. But nowhere in this case they say that they are identical. So mentioning this information over here, I don't know how this actually works out, but I do not appreciate this information. However, there is one thing that you can think about. I mean, if you are running out of time, or if your brain is not working, not giving you the information that you need, in applicable cases, let's say this exact question shows up, and you cannot think of a logical way to measure the R properly, appropriately. You can imply that we choose the two spheres to be identical, and then measure their distance between the top surface and top surface to get the R value. So you imply that for your experiment, you'll be using identical spheres. This can work sometimes, but not in all cases, because an experiment description is supposed to be working for any type of equipment that is delivered to you. Like I said at the very beginning of the P5 course, that you are trying to give instruction to a noob person who have no idea what physics is about, can read English and read labels of equipments, and gonna be able to arrange the equipments and be able to do the experiment from your instruction level. So your instruction should be empirical. It should be applicable for a whole range of setups. If you abide it, that it has to be identical spheres, then you're essentially reducing the scope of your instruction, which I personally don't like, but apparently they have allowed this mechanism. I don't know why. Anyway, we're moving on. Use calipers or micrometers to measure the diameter of the spheres and have that determined. Use calipers, use fiducial mark and ruler from the top of spheres. Okay, fiducial mark is basically using a set square so that you don't, I mean, we cannot actually place a vertical ruler on the top of the sphere. So having a set square to get that reading is basically what a fiducial marker in this case mean. You don't essentially need a set square. You can have any 90-degree edge. For example, if you have a notebook, or if you have a cardboard piece that you know for a fact is 90-degree, you can use that as well. But whatever you use, they all have to be made from insulating materials. You cannot discharge those materials while your experiment is going on. That would be wrong. Or you can use metallic stuffs before you start the experiment. Do everything measurement, and then you go for the experiment where you do not discharge them anymore. Use delta mg to determine f. So here comes the description of G that I talked about. Repeat experiment for each value of V and average F. Repeat experiment for each value of V and average F. So they've only mentioned that they have to do some sort of averaging. I explained in detail that how that averaging can be done by discharging the sphere and then recharging it and then go for the whole thing. Take reading of balance quickly to avoid discharge or keep the other charge objects away. Actually, this is a pretty important thing that I didn't say. We have to take the readings pretty fast because every charge object actually does leakage of charge. Leakage of charge means that if you have a charged sphere, let's say normally charged sphere, placed in normal atmosphere, you shouldn't expect this object to be able to hold that amount of charge over infinite duration of time, because it is exposed to atmosphere. So atmosphere molecules are continuously coming in. Because of Brownian motion, they're continuously hitting onto the charge sphere, and every single time, slowly but surely, this metal sphere will become discharged. If it is negatively charged, it will be losing electrons. If it is positively charged, it will be stealing electrons from the atmosphere. So it will be slowly losing its voltage. So to have the measured voltage from our voltmeter to be used as an appropriate value for our calculation procedure, it is important that we do the charging and the experiment within a very short distance of time. That's what they're meaning over here, that we should measure the F quickly after doing the voltage connection. And also, we should preferably keep other charge objects away, which means known objects which can produce a charge effect around should be kept further away from this experimental setup, so that you do not have external variable added to the setup that you don't know about or that you cannot measure, which is pretty unlikely for laboratory. But one thing that goes with the saying that too many people in one laboratory room shouldn't be performing this experiment at the same time. That goes without saying. If you have, let's say, 2-3 people performing in 2-3 corners far away from each other, that's acceptable. But too many people shouldn't be performing this experiment, some in simultaneous apparatus setups, in different apparatus setups simultaneously in the same room, same time. That should be avoided. Method to ensure charge on S is constant. Hold up. আজকে ক্লাস করতেছে না? ওর নাম জানো কি? শুভ্র? I haven't had a single question from him. It's pretty unlikely. What is this? Okay. কইছিলাম? আচ্ছা, না, D9. Method to ensure charge on S is constant. Example, recharge S periodically or regularly with the initial value of PD and keep S connected to a separate positive terminal. আচ্ছা, এই জিনিসটা আমি বলি নাই. I said that sphere S should be charged at the beginning and should not be hampered anywhere during the duration. But that could lead some problem because of charge leakage, which I did not think about. Yeah, this was a mistake on my part. That to make sure that the amount of charge on sphere S is correct, we should charge it periodically or keep it connected with a separate fixed voltage supply over the entire duration of experiment. This is actually pretty important. I didn't think about this, but this is a good one. This is a good one. Avoid droughts to prevent team moving. Well, in this case, for my experiment setup, this would not be an applicable way. You cannot score marks by running this one, because I am proposing that I'm going to clamp the T sphere with actual physical clamp. So dots shouldn't be able to move it anyway. But if you hang it by a thread or pendulum-like structure, in that case, dots can be logical additional detail which can be added to the experiment. But if you're clamping it, no. I think that pretty much is from my part. Any of you, if you have any question, yes, Abias, go ahead.
So are we charging both the spheres for every reading?
As per the question, this would be good, or this is recommended. But this is recommended, yes. I shouldn't say but. This is recommended. Either we should be doing this, or alternately we can do one more thing, is that we can have the bottom one continuously connected to a different supply, and then we can work with the top one.
I see, sir. So do we have to calculate the V, or is it just like?
No, the voltage that by which we're going to charge the bottom one, that doesn't have to be recorded at all as per the question. You just have to know that the charge on the bottom one is a constant throughout the experiment. That's all you have to care about. But whatever the voltage that by which you charge up the top one, you have to have a record of that. So either you have to charge the bottom one by the same value that you did start the experiment with periodically throughout your experiment. If you have a single voltage supply, for example, let's say if you charge the bottom one by 20 volt, let's say after every one reading, you should charge it once again with 20 volt, so that you can get rid of the error that could possibly be caused by the charge leakage. And also, or if you can have it connected to a separate power supply throughout the experiment. Either of this can work.
So, but one last question.
Yeah.
Would you recommend putting like small flaws in your experiment design, so you can add certain points, like certain precautions?
বুঝি নাই।
You for this experiment, you said like you're gonna clamp T, but instead, if I said I was gonna tie T to a string, I would have had an extra additional point.
Yeah. You can definitely do that. In applicable cases, you can always do that, and it is in some cases actually recommended that you do that. Yes, but it all boils down to the point that whether in that limited time of 1 or 15 minutes, can you think of this kind of ways that, well, other than writing this one, if I go for this one, I can go ahead and write this one. Thinking about this kind of alternative ways, multiple within that time, a given amount of time, is actually, in my opinion, a bit difficult. But if you can, yes, sure. I mean, one of these examples that I can bring about. One of these examples is that it's a pretty nice example, that in cases where you are about to use a voltmeter, you can always connect a CRO and be able to measure the voltage from the CRO by multiplying the Y gain into the Y-axis division. So these are usually 2 extra steps which you have to do if you're using a CRO in place of a voltmeter. They can be used alternately or interchangeably, but using a CRO can give you at least one additional detail which is relevant for the CRO, but not relevant for the voltmeter. This is a common thing, but for other apparatus, for example, for this one, I mean, having it hanging can allow you to have the D10, but having it clamped does not allow you to having it to D10. This is another thing, but this is not very common. So if you can think of it, you can definitely go for it. Yes.
Okay, sir.
Okay. আর কি করা যায়?
স্যার আজকে শেষ করে দিই।
স্যার আজকে বাদ দেন।
আচ্ছা ঠিক আছে, আজকে এই পর্যন্ত থাক। আমি একটু পরে লেকচার আপলোড করে দিয়েছি। আমি নেক্সট ক্লাসে P4 করাবো। I'll continue the lecture on the photoelectric effect. Thank you. Good night.
আচ্ছা স্যার, P4 এর স্যার ম্যাগনেটিজমের নোটস তো দেন, মানে পিডিএফ তো দেন না এখনো।
আচ্ছা এটা একটু পরে আপলোড করে দিচ্ছি, ডোন্ট ওয়ারি, একটু পরে আপলোড করে দিচ্ছি।
স্যার P5 এর বই কি হয়ে গেছে নাকি?
না, এটা এখনো হয় নাই, বলবো আমি।
স্যার ভিডিওটা একটু আপলোড করে দেন, কারণ
ওকে
একটু পার্ট।
ওকে।